Then the kernel configuration in Linux for that is called config Remoteproc, or the more specifically for the i.mx case, config imx Remoteproc. And you also need to add in the device tree certain things. It's for example, in the imx7 case, you have this imx7d CM4, and there you give it the clock, for example. This is the root clock of your M4 core. There is also a special property called FSL auto boot that will basically immediately when you boot Linux also via Remoteproc boot your M4 core. Then you can give it some memory regions, for example, for your code and for the SRAM. And another thing which I kind of scratched before, this syscon stuff, which basically means that some of the registers that are relevant to control such cores are available in the SoC in some memory area which is used for for miscellaneous stuff, and that you have to give it this syscon handle. And then the reserved memory. On the right side there you see how you can do that. For example, on imx7, these are some specific addresses which are basically reserved, meaning that those are mapped that the A and the M cores can. Then the kernel configuration in Linux for that is called config Remoteproc, or the more specifically for the i.mx case, config imx Remoteproc. And you also need to add in the device tree certain things. It's for example, in the imx7 case, you have this imx7d CM4, and there you give it the clock, for example. This is the root clock of your M4 core. There is also a special property called FSL auto boot that will basically immediately when you boot Linux also via Remoteproc boot your M4 core. Then you can give it some memory regions, for example, for your code and for the SRAM. And another thing which I kind of scratched before, this syscon stuff, which basically means that some of the registers that are relevant to control such cores are available in the SoC in some memory area which is used for for miscellaneous stuff, and that you have to give it this syscon handle. And then the reserved memory. On the right side there you see how you can do that. For example, on imx7, these are some specific addresses which are basically reserved, meaning that those are mapped that the A and the M cores can. Then a third way to do it, which is more interesting in terms of my talk, of course, is that you actually do that from the Linux side. So modern SoCs with such heterogeneous remote processors, they are often available in such asymmetric configurations. And there, basically, it allows different platforms, architectures to control, to power on, load firmware, power off those remote processors. And it also, of course, allows abstracting such hardware differences. So from a Linux kind of a user point of view, this is all transparent to the user. Then it further, of course, also adds RP message virtual IO devices, so you can actually then also communicate after you loaded your code and started it on those. You can then also communicate with those additional cores. The user API is basically, it has a call rproc boot, so that allows you to boot it. Booting meaning it loads the firmware and powers the core on. Usually, it's about clocks and power domain, stuff like that. Then it can also be powered off. There is the rproc shutdown call. So a previously booted one basically can be turned off again. Usually it does not decrement the RPROC ref counting, so it only the power ref counting. That means the user can still use such handle in a subsequent RPROC boot call again. So you could basically boot a certain firmware, shut it down again, boot another firmware, shut it down. You could even have use cases like that. And then there is another call to actually find such RPROC handle using device 3EP handle. Then how does the implementer's API look? So if you basically, are an SoC vendor and would want to implement that. So it has the RPROC alloc that allocates a new such processor, remote processor handle. Then there is a similar free. There is also a register, so it's available within the Remoteproc framework. And then there is a call so you can unroll this adding. And then there is also a way to do a crash report. So if something would go wrong, so if you have in your SoC some mechanism to detect some problem, you could also report that. There is also a call for that. And then, of course, there are the callbacks for start, stop, and there is an additional one for kick. This is mainly used when you have some communication between the cores, so you could update the other side that you want to notify it not. So it can interrupt the remote processor to let it know that in a weird queue there is something available. And then, of course, there is also a binary firmware structure. Usually, on the Linux RPROC side, it uses exclusively ELF, either in the 32 or 64-bit flavor, depending on what kind of a core you have. Then the kernel configuration in Linux for that is called config remoteproc, or the more specifically for the i.mx case, config imx remoteproc. And you also need to add in the device tree certain things. It's for example, in the imx7 case, you have this imx7d CM4, and there you give it the clock, for example. This is the root clock of your M4 core. There is also a special property called FSL auto boot that would basically immediately when you boot Linux also via Remoteproc boot your M4 core. Then you can give it some memory regions, for example, for your code and for the SRAM. And another thing which I kind of scratched before, this syscon stuff, which basically means that some of the registers that are relevant to control such cores are available in the SoC in some memory area which is used for for miscellaneous stuff, and that you have to give it this syscon handle. And then the reserved memory on the right side there, you see how you can do that. For example, on imx7, these are some specific addresses which are basically reserved, meaning that those are mapped that the A and the M cores can access these memory areas. And then this is hands-on how one can use the sysfs interface to do that. We will actually revisit that in the live demo if I happen to have enough time at the end. So we will actually be able to live on the system execute those. But it basically allows you to check the state of the Remoteproc. When, for example, you started it from U-boot, then it would have a state of attached. And then you can, of course, stop it. You can give it new firmware, which it's as convenient as just writing or copying, basically, an ELF file to some sysfs node, and then you can actually start that firmware again with echo start. And then if you started it like that, it will show as a state running. In Linux, there is the device tree binding is documented as I given it here. Basically, the first one is for the mailbox unit. Then, of course, it's a regular memory managed I/O is used for the weird I/O, and there is also the weird I/O device. And the documentation for the RP message you find in the staging part of the documentation, and the configs for it is the config imix mbox with the source code you can find there, and there is config weird I/O and config weird I/O mmio. One thing to note is, of course, depending again on your SoC, you have to make sure that whatever peripheral you might use from whatever core side, that has to be disabled or not used from the other cores in your system, otherwise bad things might happen. So, yeah, like GPIOs or UARTs or things like that. Then in the device tree, this looks as follows. Basically, that IMX7D CM4 node that I introduced before, it can also have additional nodes and properties for RP message. For example, you give it the mbox names, TXRX, RXDB, and you actually allocate which mboxes are used for that, which are then handles to the MU stuff. And of course, in the memory regions, you additionally have to add these RP message mirroring buffers. And this is how the memory for those can be allocated. And also those MUs that are referenced earlier, of course, you also have to enable, so put the status of those to enabled. Then, of course, there is also the Zephyr side, and that's actually where Open HMP comes into play, and that I'm going to discuss now. So Open Asymmetric Multiprocessing, Open HMP, that's one-to-one to this use case here. I go back here and I have the console. I actually have on the left side, this is from the A core. It's now booted into U-boot. And on the right side, oops, let's see whether I maybe, no, it should be fine. Well, it's probably just outputted some garbage from the M core. Let's hope nothing to be worried about. So from the U-boot side, for example, I can now list here, this is an MMC-based thing, so it has some files available here. For this demo, I, for example, can use this Sever Blinky ELF file. Let's have a look here. This is from the Linux side. We actually start further. We can start with that one here. So from U-boot with the bootaux command. As I'm a little bit lazy, I'm going to use the ELF file one, which usually anyway makes much more sense. Oops, I guess I might have to go here to actually select it. So I can do that one here. However, I want to use the Blinky one. Blinky. So this actually just defines that there is now a boot, so I can run. Yeah. Thank you very much. Here you go. Then we can run that, and should all go according to plan. It should start blinking. It indeed does. It has the LED here. So, and we can also look at whether it outputted something here. and it indeed did. So this is the Zephyr basically on the other UART. And then we're still in boot, in the bootloader now. We can also run the A-core side of things. For example, distro boot. Let's see. Then it starts the Linux kernel side, and I mean it's still continuous blinking, so the M4 core is still, of course, executing. And like I said, on the Linux device driver side, I made sure I'm not touching now any of his peripherals, so that core will just continue to run basically. But I set it all up that RP message, Remoteproc and RP message is all basically known now, and we can now switch to this other slide that I had here, so we can basically check what the state is of it. And like I said, when it started from U-boot, it has a state of attached, and then we can, for example, stop it. If one stops it, it now doesn't blink anymore. I actually stopped it when it's on, so it just stays on. And we can check the state again. Then it shows as offline. That's how it is done. Now we can actually copy some firmware. I have to make sure somehow it doesn't automatically mount my stuff anymore. Don't know how that happened, but I just mount it again. So this is basically the same eMMC stuff we saw before, and I can now just copy that. Let's see, from mount Zephyr Blinky. I copy that to this sysf lib firmware file. This is the default file that is used, and then we can start it up again. We just say start, and it should actually start blinking again. And if it started like that, we can check its state, and it has a state of run.